Hi everyone, I'm Xiaofei Wang. Today I'm going to present our work MetaAvatar, learning animatable closed-human models from field depth images. Modeling neural avatars as implicit functions is a rising topic in the community. NASA is among the first who proposed to model minimally closed bodies as articulated implicit functions. LEAP is a direct extension to NASA, which can generalize across different body shapes. In parallel to LEAP, ScanAnimate focuses on learning neural implicit functions for closed bodies by learning forward and inverse LBS functions in a self-supervised way. Still, with this exciting advancement, there are shortcomings of each existing approach. NASA and LEAP were designed for minimally closed bodies and do not work well on closed bodies. Although ScanAnimate works on closed bodies, it requires full body scans to train, and it trains per subject closed-type model from scratch, which takes a lot of time for each subject and closed type. In this work, we propose MetaAvatar to learn closed human body models from very sparse monocular depth frames. Following ScanAnimate, we use neural implicit functions to represent the closed body surface. It basically uses a continuous function to represent the 3D surface, and this continuous function is represented by a neural network. Since our goal is to build a closed human body model from very sparse observations, which means we need a strong prior, we use meta-learning method to learn a unified prior for how shape and clothes deform given different input poses. The meta-learned model can then be fast fine-tuned to adapt to unseen subjects. Essentially, it can generalize to unseen subjects with as few as 8 depth frames. In such a case, fine-tuning takes less than 2 minutes. We start by describing the overall pipeline of MetaAvatar. Given depth frames of a subject and their corresponding underlying pose and shape estimation, we first canonicalize the input points using learned inverse LBS functions. LBS is an standard graphics technique, and the difference here is the scaling weights are learned. Then we use the canonicalized depth points as fine-tuning data to fine-tune our meta-learned prior. After fine-tuning, we obtain this instance-specific neural avatar, and then we can generate pose-dependent closed deformations given unseen poses. Then we can apply forward LBS to get animated bodies. Here is the animated result. The canonicalized neural avatar for this test subject can be controlled by the pose input. In other words, the neural SDF is controllable or animatable. So the key contribution of this work is a meta-learned neural SDF for shape and clothes deformations. First, let's have a look how to represent these pose-dependent closed human bodies with neural SDF functions. Here we assume f is SDF function to represent the shape. This function f produces a SDF value for each coordinate point x. A naive solution to model a controllable closed human surface is to learn a conditional MLP over multilayer perceptron, which takes coordinate points and the target poses as inputs and predicts sign distance values. Here we denote such MLP as f and parameterize it by phi. X are the coordinate points in space and B are the bone transformations represented by poses and bone lengths. We tried many different MLPs, like plain MLP, MLP with positional encodings, and MLP with sign activations. MLP with sign activations works best. However, we still produces overly smooth results. In this work, instead of conditioning f function on the bone transformations, we use a hypernetwork J psi to predict the parameters of the SDF function f phi from the input pulses. So the f function itself only conditioned on the input query points, and its parameters are predicted by hypernetwork J, which takes pulses as inputs. Overall, we can obtain a pulse-dependent neural SDF. Now, let's take a closer look at the whole controllable neural SDF function f. Phi star is the meta-learned initialization of function f. It is meta-learned without pulse conditioning. Our hypernetwork is also meta-learned to take target pulses as input and predict the residuals to phi star to generate the final parameters of the neural SDF function f. Now, the final neural SDF function is controllable by the target pulses and produces nice animated closed bodies. The meta-learning consists of two stages. In stage 1, we meta-learn phi star on all training subjects with different poses, shapes, and closing types, without conditioning on poses. This meta-learned network serves as a strong shape prior. In stage 2, we meta-learn the psi on all training subjects. This meta-learned hypernetwork predicts residuals to previously learned phi star, and thus serving as a strong prior on how close deforms with different input poses. We use on-surface and off-surface losses combined with ocular regularization to train our model, such that we can train on depth points. Normal loss is used during meta-learning stage, but we do not need the normal loss for test time fine-tuning on unseen subjects. Here we show comparison to baselines. ScanAnimate uses dense full scans, and both LEAP and NASA use watertight meshes. Furthermore, all of them assume the surface normals are available. However, during fine-tuning, MetaAvatar works with monocular depth frames, no requirement for surface normals. Still, it produces very good results. Here are the results for learning with reduced data. We also present results on Kinect depth frames. Last but not least, we can also produce avatars with realistic closed deformations with a single full body scan. Thank you for watching. For code and data, please visit our project page.